Okay, we are still chapter 14. And last time we talked about kind of weak acid equilibrium and also weak base equilibrium. So remember, since these are weak acids and weak bases, they do set up obviously an equilibrium different than strong acids, strong bases when we're interested in trying to determine the pH of those things. It does require, again, an ice table here. And we do these ice tables like pretty much any other ice tables. The main difference here is at the end, we do go into our pH equation, or maybe even our POH equation. And when we do this, when we solve for a weak acid using a Ka value, that will give us the X value, which is equal to the H plus, and that essentially will allow you to go directly into that. You should remember as well as we talked about that when you do a weak base problem, right, we want to make sure we use our Kb value. And that will get us an X value that will equal not the H plus concentration, but will be the OH minus concentration, which means you probably need to go to your POH first and then use perhaps probably the easiest move, your relationship there by the 14 minus the POH to get to your pH. Remember, we also saw that if you take Ka value times Kb value, that equals Kw, which is our 1 times 10 to the minus 14 value. And that is very helpful, as we were talking about there, some problems where they will sort of give you the wrong K value, and you do need the other one, the Ka versus Kb value. And those problems are what we talked about at the very end, which are salts and hydrolysis type of problems. And the salts and hydrolysis relationship, as we talked about there at the end, is that important relationship of basically if you have a weak acid, is conjugate base will be relatively strong. And if you have a weak base, its conjugate partner there, or the conjugate acid, will also be relatively strong. So when we talk about relatively strong sort of conjugate acid and bases, what they have sort of available to them in these reactions is, again, if you take an acid plus a base, you make a salt and water. So depending on this salt, which is pretty much this conjugate guy, it will have the ability to continue to react with water. And when it continues to react with water, it will pretty much do one of two things. The salt will either take an H plus from water, and the result of that is that you will basically form OH minus, which will make the solution basic because you're producing more free OH minus in that solution. The other option is the salt itself can actually send an H plus over to water. The result of that is you will make H3O plus, which means the solution will be acidic. So these sort of conjugate acids, conjugate bases that come from a weak acid or weak base are relatively strong in that sense that they could go through this hydrolysis reaction, which is basically the reaction with water, and produce some more free OH minus or free H plus basically in that solution and will affect it. We do not get that with a strong acid or base. Their sort of conjugate partners are going to be relatively weak partners and essentially will not continue to react. So basically nothing's going to happen. It's not going to sort of react with water. It's really more neutral is sort of what we consider those salts. So these are the type of problems where definitely this guy comes into play, as a lot of times you will be given sort of the wrong K value. And remember, this is also when you write these equations, which you do have to be able to do, this is really what you're looking for to make sure that you do use the correct K value. So again, if you see on the product side of a reaction, OH minus there, and you're doing some type of calculation, you should be using a Kb value. If you see H3O plus or H plus on that side, you should be using a Ka value. So again, that is sort of how you can identify sort of which K value you should be using, as that is definitely a common error that people make is they kind of use the wrong K value with the sort of reaction that's going on. Any questions on any of that stuff there? All right. So let's get into a little bit of some specifics on these here. So, as I mentioned before, there are some salts that are considered neutral salts. And pretty much our neutral salts come from anything that's pretty much a strong acid or a strong base. And this is where, as we also talked about the other day, and again, that kind of list of strong acids, you got your HNO3, you got your HCl, you got your HBr, your HI, your HClO4, your H2SO4. So this sort of list of strong acids are good ones to know, as again, any sort of partner that comes from them basically will be weak and considered a neutral salt. And again, salts that contain anybody from group 1 and 2 on the periodic table will also produce pretty much neutral salts. That's really because group 1 and 2 on the periodic table, as we talked about, is where you find pretty much your strong bases come from. Things like sodium hydroxide, potassium hydroxide, calcium hydroxide, and so forth. So that kind of group 1, group 2 is pretty much your strong bases. And obviously here's your strong acids. So anything that comes out from these guys, like this particular salt here, sodium chloride, this guy and this guy, that is group 1. And most likely came from sodium hydroxide, which is a strong base, which means this is going to be relatively weak. Cl minus most likely came from which acid? Hydrochloric acid, most likely, yes, since it has a Cl in it. Yeah. So that's a strong acid, and that's going to mean that this guy's going to be relatively weak. Here we would expect this to be a neutral salt, and the pH here would be 7 in this particular case. Any questions on that one there? So sometimes when you're dealing with a salt and you're trying to figure out, does it go through hydrolysis, or if it does go through hydrolysis, sort of what will happen. One of the good things to sort of think about is where that salt came from. Try to think about what acid-base combination maybe came together to make that salt. And that oftentimes can help you sort of decide what's going to go happen if it's going to kind of continue on to react. So now we do have basic salts. So if we took something like, say, sodium acetate, yeah. So sodium acetate here, when it's in solution, which is a salt, will break apart basically into sodium ions and acetate ions here. Now, again, we want to kind of think about probably where did sodium acetate come from? Where did this salt come from? What combination of like an acid and base would get me there? You probably could imagine that the base was maybe something like sodium hydroxide, right? And acetate most likely came from what acid? The acid name, if the polyatomic ion ends in ate, ends in ic, so acetic acid, perhaps, it would be where that most likely came from. And that is this guy here. Acetic acid here is a weak or strong acid? Well, that's my list of strong, and I don't see it on there. So I'm going to assume that it's going to be weak. Yes. If you don't know that, by the time we're done with this chapter, you definitely will know that. Yes. So acetic acid is definitely a weak acid. So we have a weak acid, and we really have this guy, which is a strong base. So when we think about the salt that breaks apart, the sodium ion, should I be worried at all about the sodium ion here in terms of hydrolysis and reacting with water? I should not, because that again most likely came from sodium hydroxide, which is a strong base. It's also part of group 1. It is pretty much going to be neutral. It's not going to be doing anything there. But when I look at acetate, that came from my weak acid here of acetic acid. Should I be worried about that? I should, because it comes from a weak acid, which means this is going to be relatively strong in the sense of reacting with water. The other thing that helps you maybe figure out what happens is Because it comes from a weak acid, that means technically speaking, this is its conjugate base, right? So oftentimes people have trouble figuring out what will it do when it reacts with water. So if I take my reaction here of my acetate, and it's going to go through a hydrolysis reaction, which means it will react with water. Because it's actually a conjugate base, all I have to do is a definition of a base, which means it's going to accept the H plus. And when it accepts the H plus, it will always make, by the way, where it comes from, which is acetic acid. And in this case, it will produce hydroxide. So because this reaction will produce hydroxide, we should expect the solution to be acidic, basic, or neutral. Should be basic, right? Because we're producing hydroxide. By the way, when we do a calculation with this one and we lay up an ice table, what type of K value should I be using? Ka, Kb? Should be using a Kb value here. And most likely in the problem, you'll have the Ka value for acetic acid given to you. So again, these are the problems where they typically will give you sort of the incorrect K value, if you want to think about it that way. And obviously, this is where we would use our Ka times Kb equals Kw to kind of flip it around to the value that we need. So any type of salt that originated from a weak acid will go through hydrolysis. It will react with water. The end result of that is it will always produce hydroxide because it's always going to act as a base and accept the H plus from the water and produce that OH minus. And again, if we wanted to solve for the pH here, we would need to do an ice table, right, with the equation that we have on the bottom. We would need to make sure that we got it to the Kb value. The deal here, though, right, is when we solve for X, X is going to equal the hydroxide concentration, right? So that will allow you to get the POH, and then you would have to get the pH. So we can't get the pH directly, obviously, from that calculation, but we can't get the POH and then get to the pH. Any questions on that there? Okay. Now, there are also salts that are acidic and considered acidic salts. And something like ammonium chloride, for example, here. Ammonium chloride is a salt that, again, when it goes for a swim, will break apart into NH4 plus and a little Cl minus action happening there. So again, it may be beneficial to try to think about where basically this salt came from, what combination of like an acid and a base maybe got me there. If you had to guess, the acid most likely is HCl, yes. So that is most likely your acid, and that's probably the source of where the Cl minus came from. NH4 plus most likely came from what base? What looks just like that? NH3, ammonia, which is a weak base, right? So this is probably your combination here of acid and bases that produce this salt here. And again, that can be helpful when we're looking at this salt to help us determine if there's going to be any type of hydrolysis that's going to happen. Well, we clearly know, hopefully, that the chloride, which comes from this strong acid, is going to be relatively weak and really a neutral salt. So that's not going to basically do anything. The NH4 plus comes from a weak base, which means will go through hydrolysis. It will, right? And because it comes from a weak base, this is the other part that's kind of helpful. I know that technically speaking, this is going to be like the conjugate acid, right? And this guy is going to go through hydrolysis. And knowing that it's basically like the conjugate acid, that is again going to help you, hopefully, when you write the reaction of ammonium plus water, to understand what's going to happen, which is it's going to act like an acid. And the Bronsted-Lowry definition of an acid is it's going to send the H plus over there, basically to the water. The result of that is, once again, as you can hopefully see a pattern, you will always produce where it came from. So that salt will always produce basically where it came from. It came from NH3, that's what we produce. And in this case, when the water gains that H plus, we are going to produce H3O plus. And once again, that sort of production right there will basically tell us that it is going to be an acidic solution because we're obviously producing H3O plus in that solution. Again, here, if we were going to do some type of calculation, that is going to be a Ka value that we want to use in this case. Once again, in this type of problem, you most likely will have the Kb value for NH3 given to you. If they give you anything at all, you might have to go look it up in the book, but if they give you, typically they will kind of give you sort of the opposite Kb value or Ka value, depending on which one you're looking at. So this is considered a acidic salt. You will always get an acidic salt if the salt comes from basically a weak base. And when it comes from a weak base, it will always create a salt that's basically the conjugate acid, which will always donate the H plus to the water, and you will always basically produce H3O plus in that solution, and it should be acidic. Any questions on that there? Now, there is also another way that you can create sort of an acidic salt, and there are certain metals, for example, certain metals here, maybe. There are certain metals that are highly positively charged, like a lot of times +2, +3s, etc., that actually can go through hydrolysis. So, for example, when we have something like, say, the aluminum ion here, and we write aqueous next to it, what it basically means is there's water surrounding this guy. And we would have something like this in terms of its formula. That's kind of what the aqueous sort of means. It's like there's water molecules basically surrounding it. So what happens in a situation like this is we have the aluminum and it's attached to basically 6 waters. And I'm just going to draw out one of the waters only. By the way, the waters are attached to the oxygen here. And I'll just draw one water out like so. So what happens is you have this really complex ion floating around here in this solution. And what's going to happen actually is another water, not attached to it, just another water kind of floating around, will essentially accept an H plus there from this complex ion. The result of that is this other water will now pick up basically an H plus and become basically H3O plus, right? Hydronium ion. And the result of that is, if we just look at what happened here, we still have basically all 5 of these waters still intact, right? But we did lose one of the H's off the 6 water, which gives me an OH minus basically left over. And that's going to give me a funky looking guy like that in terms of what's produced. But in terms of what we're talking about here in terms of the salts is we are going to produce H3O plus, which once again will basically be an acidic sort of salt. So small metals that have sort of big positive charges, +2s, +3s, a lot of transition metals can do that. So a lot of transition metals have the ability to sort of do that. They will produce H3O plus in this type of reaction. Basically, one of the waters attached to the metal will lay up a hydrogen over to another water, and it will make H3O plus and make an acidic solution. So that's kind of 2 ways that we could kind of get an acidic solution here in the salt realm. Basically, anything that comes from a weak base are certain metals, especially transition metals, with positive charges, +2s, +3s, have the ability to also produce H3O plus in solution. Any questions on that there? All right, so let's take a look at some here. What is the pH of a 0.45 molar? Okay, so let's take a look here. This is obviously a salt, right? And again, because it's a salt and obviously potassium's there, this is going to be a strong electrolyte, and in solution is going to break apart 100% basically into these ions that are floating around in this solution. And again, if you're not sure, you might want to think about maybe what combination gave us this guy. And K is most likely KOH, which is a strong base. And once again, the Cl minus that we've seen before, again, most likely came from hydrochloric acid, which is a strong acid. That means that this guy here came from a strong base, which means it's going to actually be neutral, right? It is not going to be strong at all. It's going to be weak and not react with water. This guy here, which came from obviously our strong acid, also is going to be weak and will not go through hydrolysis, which means he's also going to be neutral, which means there's actually no calculation here. The pH here should be 7 for this guy, as that is considered a neutral salt. Any questions on that there? All right, so now that we saw one that's neutral, let's do one that does involve a calculation. So why don't you give this one a go? Considered 0.3 molar sodium fluoride. Ka value for hydrofluoric acid is 7.2 times 10 to. Okay, let's take a look here. So again, a couple things when you're doing these problems that you want to make sure that you look at is not to miss too much important information in here. So first off, we have NaF, which is a salt, and we know that this salt here should break apart into sodium ion and a fluoride ion here. Again, we want to think about where these guys came from. This is really, again, group 1, which comes from a strong base, so we don't really have to worry about that going through hydrolysis. This guy, if you're not sure, they also give us a Ka value for HF, most likely came from HF, which is told us in the problem. The other thing that they tell us in the problem, basically, that's the Ka value for HF, which means that's a weak acid, which means that this guy definitely should go through hydrolysis here with some water. So it's going to react with water and do a hydrolysis reaction. That also tells us, because that's the Ka value for HF and that's an acid, that F minus is most likely going to be its conjugate base, right? So now we know that it's going to act as a base when it reacts with water. And now we can write our equation here, which is F minus plus the water. And again, knowing that that is going to be a base, and logic also tells us it doesn't have an H to give, so it can only accept in this case. It's going to accept the H plus. The result of that, as I mentioned before, is it will always form where it came from. So they kind of give you where it comes from. So you pretty much have your entire equation pretty much right there. That's going to produce OH minus as well. Any questions on how I get the reaction there? So again, there's a lot of information kind of stored in the problem itself. Make sure that you just kind of bypass that information. It can help you with what a lot of people struggle with, which is writing the equations, because a lot of times you actually have pretty much your stuff from the equation in the problem. Once we do this here, we could do an ice table. And as you hopefully know, since it's all a 1-to-1 relationship between these two, the concentration of the F minus will also be 0.3 molar, as again, it's a 1-to-1 relationship. So that would be 0.3. That would be 0 and 0. Change here, minus X plus X plus X means at equilibrium here. 0.3 minus X, X, and X. Any questions on the ice table here? This will go into my K expression, which is my products in this case, divided by my reactants. This is a K, A, B, C, D, E, F, G. This is a. It is a KB I need, right? Because I have hydroxide. By the way, before I even finish the calculation, my pH should be acidic or basic. Should be basic. So these are all the things that you know before you even type it into your calculator. Because you're producing hydroxide, you should end up with a basic pH. And because of that, I need a KB value. And that is what the expression I have down there is. So that is where we're going to use our Ka times Kb equals our Kw. That means that my Kb in this case would be my Kw, which is 1 times 10 to the minus 14, divided by my Ka in this case, 7.2 times 10 to the minus 4. And that's going to get me here. Oops, if I hit the right button, so get me something. Try that. There you go. And we'll call it 1.4 times 10 to the minus 11. So that is what this should equal. So putting in our equilibrium like normal gives us x squared 0.3 minus x. That obviously is a small value of k, which means we can make an assumption in this case. So because this is small, we could assume x is equal to 0. And that's going to then give me basically x squared divided by 0.3 equals 1.4 times 10 to the minus 11. I'm obviously going to multiply to the other side, and then I'm going to do a little square root action on it as well. So we'll times it by 0.3. We'll then take the square root of it, and we will end up with a number. I don't want to count zeros, so I'm just going to call it x is equal to 2.04 times 10 to the minus 6. Remember that we did make an assumption here, so we do need to check it. So to check our assumption, we're going to divide this by 0.3, times it by 100%. And again, we're still going with the 5% rule like we've done before, and we're nowhere even near 0.1%, so the check is good here. So that means that if we go to our ice table here, that X does equal the OH minus concentration. Again here, not the H plus concentration. So our concentration of OH minus is going to equal 2.04 times 10 to the minus 6 molar, which is basically what X equals in our table. That going into our POH. Is going to get us there minus the log of 2.04 to the minus 6, a 5.69. Again, if by some chance you got a little confused and you thought that that was your pH, again, should not make sense because it should be basic, obviously, right? So here to get to the pH, we're going to take 14 minus our 5.69. And that will get us here 8.31 as our pH, which is a basic pH and what we would expect in this case. So the sort of guts of the calculation here is pretty much like a normalized table. Again, you can make your assumption if you want. You could quadratic. You could solve it any way you want. But where most people again struggle with these type of problems is writing the equation and using the correct K value. So it's a very common errors that people make. Any questions on any part of that there? All right, so let's try another one here, see what you come up with, maybe. If I stop striping lines on that. All right, let's try this one here. Calculate the pH of a 0.75 molar aqueous sodium cyanide solution. The Ka value for HCN is 6.2 times 10 to the minus 10. Idea, we have a salt, and that guy, when it's in solution, obviously is not going to stay together and will break apart into its ions. And once again, we want to sort of analyze the ions here and see if we're going to get any type of hydrolysis is going to happen, reaction with water from the salt. Once again, we've seen sodium a number of times. Group 1 also comes from probably sodium hydroxide. We really don't have to worry about that, as that guy is pretty much a neutral salt. Our CN minus, once again, if you're not sure, we want to look at the other information given to us in the problem, and we do see a Ka value for HCN, which would imply that this is a weak acid, and that HCN does seem like it's related to that guy, as the only difference is one H plus, which means that that is going to be really his conjugate base. And will go through hydrolysis because obviously it comes from here a weak acid. So this guy here will go through hydrolysis, and the reaction that we're going to get is the CN minus plus the water. Once again here, logic tells us it doesn't have an H, so it can't give it. It's got to accept it. We also know that is what a base does, is it will accept an H plus here. And as I mentioned before, if you're not sure what it produces, also quite helpful, it's right there. That is what it produces. It will always produce where it came from. And once again, in this case here, we will produce hydroxide. So again, without doing the calculation, this pH should be basic, right? And we also should be using a KB here, right? Because of that hydroxide. So pop it into our ice table here. We will have 0.75 molar CN minus 0, 0. Obviously, we do not going to worry about water like normal. So just going to leave it alone, as it's not included in the equilibrium. So we'll get a pretty traditional here ice table, 0.75 minus X, X, and X at our equilibrium line. Any questions up to there? That will then go into our KB expression, which again is going to be our products. Bless you. And obviously here we do not have a KB, but we have the Ka. So we're going to do our little flip around here. Going to use Kw, 1 times 10 to the minus 14 divided by the Ka value, 6.2 times 10 to the minus 10. And gonna get us something here. To the minus 10. Looks like maybe 1.6 times 10 to the minus 5. So that is what we'll use. 1.6 times 10 to the minus 5 will essentially equal X squared from our products over our reactants. Why not? Might as well make an assumption. And I'll be honest with you, a lot of times you're going to be in good luck on these. They're going to work probably in most cases. So that's going to get us X squared divided by 0.75 equals 1.6 times 10 to the minus 5. Just like last time, I'm going to multiply and then square root it. And that will get us here 0.75, a little square root action there. Going to give us basically an X value here of 3.48 times 10 to the, looks like negative 3. We do want to check it. So once again, we're going to divide in this case by 0.75 and times it by 100 to check it. And we should be good. Like I said, usually you're pretty good. 0.4% here. 0.4%. So check is good in this case. Once again, we did produce hydroxide. So that is what the X value is going to equal. So the concentration of hydroxide in this case, 3.48 times 10 to the minus 3 molar, as that is what X equals. Going into our POH equation here, minus the log of 3.48 times 10 to the minus 3. Going to get us here 0.4 to the minus 3. Looks like 2.47. Remember again that that is your POH. So our pH would then equal 14 minus our 2.47. And that's going to give us a more basic pH that we're looking for of 11.53 in this case. Any questions on that there? Yeah. Questions. So salts, if they do go through hydrolysis, will basically require an ice table. Again, those are things you want to watch out for. The K values, writing the equation correctly. The other thing, like I said, that people struggle with is writing the equations For example, some people would write this equation where it produces H3O plus rather than OH minus. So you want to make sure that you do write it correctly so that it doesn't affect the calculation that you have to do. By the way, if we had an acidic salt, it would work the same way, ice table. The only difference is when we solve for X, that would be the H plus concentration. So we could go directly into the pH equation rather than the pOH equation like we did on these. Any questions on hydrolysis of salts here? All right. So up to this point, we looked at salts where basically only, and here's a prettier picture of the aluminum going through hydrolysis here, but we only looked at salts where one of the ions would go through hydrolysis. It is possible that you could have a salt, say like ammonium nitrite. Ammonium nitrite is ammonium and nitrite, right? Ammonium, as we saw, comes from NH3, which is a weak base, which means this guy will go through hydrolysis, as we saw earlier. NO2 minus most likely comes from what acid? HNO2, yeah. That is nitrous acid, not nitric acid. That's nitrous acid. That is a weak acid. So will the NO2 minus go through hydrolysis? It will as well. So it is possible that you could have a salt where actually both parts will go through hydrolysis. The calculations is kind of crazy if you try to do it both separately. So in a situation like this, if you happen to come across a salt where you're like, I think both of them will go through hydrolysis, what we do is we actually compare the Ka value to the Kb value, and whichever one is larger, that is pretty much what we predict the salt would do. So for example, if the Kb value for the anion is larger than the Ka value for the cation, then we would assume that it would be basic, and we would do the Kb calculation. If you look at it and the Ka value for the cation is larger than the Kb value for the anion, then we would assume that the solution would be acidic, and we would do the Ka calculation. If you find yourself where the Ka and Kb value for that salt, cation and anion is about the same, then it is going to be neutral, right? A pH of 7, if they're about the same. So here's a table that sort of describes what we've been talking about, but again, it is possible to come across a salt where both parts will go through hydrolysis. So what you want to do is compare the appropriate Ka and Kb values, and whichever one is larger, that is what you would predict would happen in solution, and that is the calculation that you would do. Any questions on that there? All right. So let's talk a little bit about oxides. Oxides are elements, obviously, that contain oxygen. And there are some basic oxides, which is like group 1 and 2 on the periodic table. Basically, these basic oxides, if you react them with water, will essentially produce bases like sodium hydroxide, potassium hydroxide, and so forth. Over here, where our nonmetal oxides are, those are typically our acidic oxides. So if you take something like water and our friend CO2, you will make carbonic acid. So a lot of those acidic oxides, if you react with water, will produce acids. Like if you take the one I scribbled on there, N2O4, and react with some water, you'll get some nitric acid that will come out of it. And there's also some amphoteric type of oxides. And amphoteric, as we talked about earlier in this chapter, is something that could act as an acid or a base. So they could kind of go either way when they react with water in that situation. So let's talk about another definition of an acid and base, which is an important one. And we definitely will see this definition a little bit later on in a chapter 19-ish or 20, somewhere in that ballpark. We talked about the Arrhenius definition of an acid and base, which is something that would produce H plus in solution, and a base obviously would produce OH minus. The Bronsted-Lowry acid is something that will donate an H plus, and a base is something that will accept an H plus. Our friend Lewis didn't want to be left out. When we think of Lewis, we think of Lewis structures, and when we think of Lewis structures, what things are involved in Lewis structures? Those are, you draw Lewis structures with electrons, yes, valence electrons. So it's not surprising that Lewis's definition of an acid and base actually involves electrons. So a Lewis acid is actually a substance that will accept a pair of electrons. So a Lewis acid is something that will actually accept a pair of electrons. A Lewis base is something that will donate a pair of electrons. So the Lewis acid definition of a base is something that we use a lot when we talk about transition metals and complex ions being formed and how things happen. So if we look at this here, these couple of examples, here we do have our H plus, right? So what makes something a good Lewis acid is something that can accept a pair of electrons, and usually things that want to accept a pair of electrons are things that are electron deficient. And those are things with like positive charges, right? If you're a positive charge, you lost some electrons. So in that case, you like to gain some electrons. What makes something a good Lewis base is it is usually apolar or has an unpaired lone pair that it can donate that has negative charges. So in this case here, he's going to donate some electrons over, and that's going to be our Lewis base. And this here would be our Lewis acid as it's going to accept it. Also, you can still do the Bronsted-Lowry definition of that, right? He's going to donate the H plus over, which makes it the acid and this the base. It ends up the same definition, rather acid and base will be the same thing. Here again, we have our deficient sort of hydrogen, which will make our Lewis acid. This is NH3, which is a polar molecule, also has some non-bonding electron pairs right there on the nitrogen that it can donate over, which makes it its Lewis base. Same idea though, if you take the Bronsted-Lowry definition and donate the H plus over, that's the acid, and obviously NH3 would be the base. So you do get the same sort of result of what's an acid and what's a base, but again, one looks at protons in Bronsted-Lowry, Lewis acid and basis looks at electrons being transferred. So typically things with non-bonding electrons and our polar molecules, things like water is also a Lewis base. NH3 is a Lewis base, Cl minus, all these things are Lewis bases. Now, where Lewis bases really come into play really well in terms of acid and bases is you could apply acid-base chemistry to something that does not involve a hydrogen, H plus, being transferred or accepted. In this case, there is no hydrogen that's going to be transferred, but we have boron, which, as you might know, is an incomplete octet, right? It has less than 8 electrons, and it is definitely electron deficient because of that. It has less than that. So it's going to definitely want to accept those electrons there from the NH3, which would make this my Lewis base and my Lewis acid here. And this is a nice example of you could actually apply acid-base chemistry to something that does not involve no hydrogen transfer here, right? And you could still apply sort of something like acid-base chemistry to it. Any questions on the Lewis acid-base combination? We definitely will see Lewis acid and bases pop into a couple places along the way. And when we get to that one chapter there with transition metals and coordination complexes, we will see them again for sure. Any questions on that? All right, so not all acids are monoprotic, right? There are diprotic acids which have 2 hydrogens that it could give. There are triprotic acids, which have 3 hydrogens to give. So we have monoprotic, 1 hydrogen. We have diprotic, 2 hydrogens, and triprotic, which is 3 hydrogens. Remember, for each of these, if you ever need a formula, you could use a generic sort of formula like HA for monoprotic. By the way, that's H plus and A minus are the ions that are present. You could use H2A for a diprotic. That is H plus and A with a -2 charge. And you could use H3A here for triprotic, which is H plus, and the A actually has a -3 charge, which is why there's 3 hydrogens, obviously, in that. So hydrogens do come off basically one at a time. So they, again, do not just all drop off at once. So if you had something like phosphoric acid, which is a weak acid, the very first thing that would occur with phosphoric acid is it would lose 1 hydrogen and make H2PO4 minus. By the way, there is a Ka value for that, which is known as the Ka1 value, as you can see on this table, and it's something like 7.5 times 10 to the -3. The next thing that would happen is our H2PO4 minus, or actually here in this case, will then lose a second hydrogen and become HPO4 2 minus, right? Just 1 hydrogen at a time. Ka value for that, which is the Ka2 value, 6.2 times 10. I think that's a -8 in that case. And lastly, what would happen here is this guy that's already dropped 2 hydrogens will go and drop his third hydrogen and become PO4 3 minus. Ka3 in this case there, 4.8 to the -13. Is it harder or easier to remove the second hydrogen versus the first one? Which one is easier? It is the first one is easier to remove because after you remove it, you now have something that's negatively charged and you're trying to rip off something that is positively charged, right? So it's going to hold it a little tighter. Gets even harder to try to rip off the third one. I could see that that is the case because when I look at Ka1 versus Ka2 versus Ka3, what happens to the Ka values as we keep taking off a hydrogen? Do they get larger or smaller? They do get smaller. And when the K value gets smaller, that means I have more reactants or products. Reactants, right? And if I have more reactants in the second and third equation, that means I'm not losing a lot of H plus, right? Not a lot of H plus is coming off. So it gets harder and harder every time you try to remove a hydrogen. Less and less of the H plus comes off every time you remove one because it gets, again, very much harder to do so. That is typically what we see in the Ka values as we go from Ka1 to Ka2 to Ka3. We do see a decrease in it, which means it's basically staying together. Not a lot of it's coming apart, and we're not producing a lot of H plus in that case. Questions on that there? So let's say we wanted to do a calculation and figure out the pH here of these guys of a, say, phosphoric acid solution. So let's go through a calculation, and we'll get to that here in just a second, I think. Let's go through this calculation here where we're looking to solve for everything, basically. We want to know what is the pH of a phosphoric acid solution that's 5 molar. We want to know what is the concentration of phosphoric acid at equilibrium, H2PO4 minus at equilibrium, HPO4 2 minus, phosphate, and H plus at equilibrium. By the way, just why we always think about maybe the overall reaction, right, is if I add these guys together, this cancels, right? This cancels. And I'm left with H3PO4 that goes to 1, 2, 3 H pluses, right? And phosphate. So most of the time, like in Chem 50, you just kind of look at the overall equation where you see all three of them coming off, and it implies that they're all coming off at once. But again, it is a stepwise sort of fashion as to all those guys coming off. All right, so back to the problem here. All right, so we've got our three K values here, Ka1, Ka2, and since we're looking for everything here, we're going to start with our first hydrogen that comes off. So that would be the equation we wrote previously, H3PO4. It will lose one hydrogen and make H2PO4 minus. That is going to be our Ka1 value that we see there, 7.5 times 10 to the minus 3. Now, we're going to do an ice table here. So we're going to take our initial concentration of our phosphoric acid, which is 5. These are going to be zeros. Change here going to be minus x, plus x, plus x, which means at equilibrium, we have 5 minus x, x, and x. Any questions on that table there? We're going to put this into our Ka1 expression, which is our products, which is H plus, H2PO4 minus divided by H3PO4. That's going to give us basically x squared divided by 5.0 minus x equals our Ka1, 7.5 times 10 to the minus 3. So in this particular case, I'm going to assume that x is equal to 0 and give it a go. And that's going to give me x squared divided by 5 equals 7.5 times 10 to the minus 3. We're going to multiply and then square root. And if we do that there, we will take 7.5 to the minus 3 times 5 and then square root it. Maybe just square root it once would be good there. Try that. All right. And that's going to give me an x value here of 0.194, we'll call it. We do want to check it, so we'll take our 0.194, we'll divide it by 5, times it by 100%. And in this case here, we end up with 3.9%, which is good. Probably why I changed it to 5 molar when it was originally 2, and it was not good idea, but this is good. So off of this, we actually have some answers to our question here, right? We could see from the ice table there that x equals, in this case, the concentration of H plus, which would be 0.194 molar. X also equals from that table the concentration of H2PO4 minus, which would also be 0.194 molar, and also our phosphoric acid concentration will equal 5 minus x, which would be 5 minus 0.194, and that's going to get us there 4. We'll call it 4.81 molar. So off of my very first ice table here, where my H pluses were coming off, I have now calculated the concentration of this guy, and really this guy. Any questions off of that? I am still looking, though, for the concentration of HPO42 minus, which means in this case, I only see HPO42 minus right about there is where it starts to come out. So I do need to look at the second hydrogen coming off equation so that I could get to that based on the question here. So if I do that, let's take a look at that. We'll turn pages. There we go. So because we're looking for the next one, we're going to look at the next association, which is this. It will give off that H plus and that HPO4 2 minus in this case. This is going to be our Ka2 value, right? Which is 6.2 to the minus 8. Now, when I go to do this ice table here, And again, I do need to do it because I'm looking for some other information here that was not solved from the first table. Do I have a concentration of H2PO4 minus at this point? The answer is I do, because it is right there, right? So we do have some of that to start with. We also have some H plus also floating around in that solution at this point. So we'll take a look at that here. So that was 0.194. We also have 0.194 this, and we have 0 that. So in this case, we do have some starting amount of that. That's obviously still in the beaker floating around in the solution. So our equilibrium line from our first table becomes kind of like our initial concentrations on the next table. The rest of the ice table is going to be the same, minus X plus X plus X. This is going to give us 0.194 minus X, 0.194. Remember, this is actually plus X here, and that is X. Going into our Ka2 expression of products divided by reactants. Put it in our values, gives me 0.194 plus X times X divided by 0.194 minus X equals our Ka2 of 6.2 times 10 to the 8. The assumption worked good on the first one, so why not try again? So I'm going to assume that X is equal to 0. That is going to reduce this down to 0.194 times X. We would be getting rid of any X's we're adding or subtracting a number from. Those are the X's we're getting rid of. And that would be 0.194 equals 6.2 times 10 to the minus 8. I think I could do that math. Those cancel. And that's going to give us an X value of 6.2 times 10 to the minus 8. Clearly here we should check it. So we'll divide it by 0.194 times it by 100% to check it. And I think we should be fairly safe in this case here. Not even 0.1%. So the check here is good. Any questions on that there? At this point, this will give us a little bit more information. This will now give us another piece of information that we're looking for, which is the concentration here of our HPO4 minus, and our HPO4 minus concentration, if we add it to our list here, will then be our 6.2 times 10 to the minus 8 molar. And that gives us this guy. Now, when we look at, by the way, the H plus concentration at equilibrium and our H2PO4 minus at equilibrium, when I put my X value back into here, what do I end up for those guys? I will still end up at 0.194. So if you do those, you'll basically still end up at 0.194 because you're subtracting and adding basically 0.7 zeros and a 6, right? So way out there, yeah. So it's not going to actually change their concentration. Basically stays the same at that point. So if you punch that into your calculator, 0.194 plus 6.2 times 10 to the minus 8, you still get 0.194, yeah. And it doesn't really change for either of those guys. Any questions on that there? Now, that was good. We got the there. In this particular problem, because we're also interested in phosphate, that only comes out there with the third hydrogen. So we will need to do the third dissociation here, or the third hydrogen coming off. So that is what we want to kind of do here with our third one. And if we do that, it will look something like this here, I think. We will have our HPO4 minus will then lose its last hydrogen here. And that is where we will actually form the phosphate we're looking for. And this obviously would be our Ka3 value that we would get from the table. Looks like 4.8 times 10 to the minus 13. Once again, when we go to the ice table here, we need to look back at our equilibrium line, and we do have some values here. We again have our value for this guy from our equilibrium line of our previous table, And as we saw, our H plus really hasn't changed all that much. So we have that guy. So that's going to give us initially here 6.2 times 10 to the minus 8 molar, which is what we got on that last table there. Zeros, not zeros. We do have an H plus, as I just got done saying a second ago. And that H plus, as we saw, didn't change all that much. It is still 0.194 molar as what we had on our equilibrium line. Change here going to be minus x, plus x, plus x. Going to equilibrium it there, 6.2 times 10 to the minus 8 minus x, 0.194 plus x, and x. This will go into our Ka3 expression of our products divided by our reactants. And that's going to equal, in this case, 0.194 plus x times x divided by 6.2 times 10 to the minus 8 minus x equals 4.8 times 10 to the minus 13. Why not? We're on a roll. We'll still assume x is equal to 0 in this case as well. And that's going to reduce this down. Once again, our x's we're adding and subtracting from 0.194 times x divided by 6.2 times 10 to the minus 8 will equal 4.8 times 10 to the minus 13. We're going to multiply 4.8 times 10 to the minus 13 there, minus 13, times 6.2 to the minus 8, and then we're going to divide by 0.194, and that is going to give us an x value here, 1.5 times 10 to the minus 19. Again, we want to check it, so we'll take it maybe by the bigger number there. It don't really matter, I think. So if we divide it by 0.194 times it by 100, we are good again with the check. So that will give us what we're looking for, which is, in this case, really the phosphate. And that would be our concentration of phosphate, which I guess we could add to our list here. Our phosphate would be 1 point, what I got there, 5, I think it was, times 10 to, whoops. What was that? To 19, right? By the way, with this, if we take this x value and put it back into here, did my concentrations change? No, because it's super small, right? So it's not going to affect those concentrations. So we have to 19 there, I think. All right, so 2 to 19. And at this point, we have now solved for everything we're looking for except for the pH. Now let's talk about the pH. The most H plus came off in which step? After the first step, we had 0.194 molar H plus, right? On the second step, we basically had that much come off, right, of it, which is not a lot. And on the third step there, we had about that much come off, which is even less, right? So the majority of all the H plus came off in the very first step, which also shows that it is much harder, right, to rip off those second and third hydrogens in this case, and less of it comes out, which is why we do see those K values get smaller and smaller as we go from Ka1 to Ka2, Ka3. That means that when you're doing any type of diprotic calculation, triprotic calculation, polyprotic calculation, and you're only interested in the pH, unlike this problem where we're interested in like everything. But if you are only interested in the pH, it is probably safe to just do the pH calculation off the first table and the first hydrogen coming off, since that will most likely be the majority of the H plus that comes off. So in that case, just like here, that would give us minus the log. It was 194, I think, 0.194. And that would give us, in this case, a pH 0.194. about a 0.71 pH, pretty acidic. But in the case of polyprotic acids, pretty much most of that hydrogen is going to come off in the first step. So again, if you're really only interested in the pH, just calculate from the first step and you'll probably be fine. If you have to calculate something like everybody, like here, we only really had to go to the third step because we were interested in phosphate, right? So that's the only reason why we really had to go all the way out to the third step to calculate that concentration. Any questions on polyprotic acids there? Yeah. It did, because even all the way down to the third ice table, if we put in our X value, is still 0.194. And it pretty much didn't change. So the majority, if not almost 100% of it, not all of it, obviously, a little bit still coming off, but almost 100% of the H plus that came off in the very first ice table that we did here. And that's what I was saying. If you're just interested in the pH, you pretty much in a polyprotic acid could just lay up that first ice table and probably be pretty safe in your calculation of pH based on how much H plus comes off of it. Other questions? All right.